Hello everyone and welcome back to Teach Astronomy. My name is Victoria, but you can call me Vicky. And today is Monday and we're starting a little early today because it is today because I know the schedule's been kind of weird lately, but I am balancing many other jobs and I just want to make sure that we actually ever get through this book. So today we're going to be reading chapter 9, but technically 10 if you count the introduction. It's like part 10, I guess, about Chandra, exploring the violent cosmos. And I think we're just going to jump right into it. Hope everyone here is having a good day. And we'll chat. I'm sure we'll chat. We've got a couple hours. But yeah, we'll just jump into it. All right. Exploring the violent cosmos. When we dream of other worlds, our dreams may be vivid and real and colorful, but they're subject to the limitations of our senses. To visualize something... Oh, thank you for that follow, Shahana07. Welcome to the channel. Welcome to Teach Astronomy. To visualize something, even if in our own mind's eye, we use the visual sense. For most of the history of astronomy, we learned about the universe exclusively through visible light. Tens of thousands of years of naked-eye observations were followed by the first nighttime use of the telescope by Galileo in 1610, followed by a steady march of successively larger telescopes, culminating with the 8-11 meter. Oh, 8 to 11. I was like, that seems like a really technical way to talk about a telescope. Culminating with the 8 to 11 meter behemoths of the present day, with dreams of even larger ones to come. The historical focus on visible light was natural, since the most powerful human sense evolved to match the peak energy output of our life-giving star. The cool outer envelopes of stars emit most of their radiation in the visible range, and galaxies are just assemblages of stars. The night sky is visually rich. About 6,000 stars are visible to the naked eye at a dark site, but they are just an infinitesimal sliver of the stellar plenitude of the universe. We live in a system of 400 billion stars, and the observable universe contains roughly 100 billion stellar systems, for a staggering total of 10 to the 23rd stars. Also, the spectral transitions that are the fingerprints of different types of atoms fall mostly in the visible wavelength range. Cosmic chemistry is practiced with telescopes that gather light and disperse it into its constituent wavelengths. Nevertheless, just over 200 years ago, experiments showed there are wavelengths longer than the reddest waves of light and bluer than the bluest waves of light. 100 years later, Wilhelm Röntgen performed the first systematic experiments to understand the nature of mysterious radiation that was generated by high-energy particles moving in the vacuum of a sealed glass tube. In 1895, he announced the discovery of X-rays. The details of the discovery are poorly documented because Röntgen had his lab notebooks burned when he died. X-rays electrified the scientific community, and within a year, the potential for medical imaging was realized. It was a lot longer before anyone discovered that they could be used for astronomy. Röntgen received the first Nobel Prize ever awarded for physics in 1901. Just as X-rays provided a window into the human body, they now provide a window into space onto worlds barely imaginable. X-ray telescopes have revealed the nature of black holes and neutron stars for the first time. They've discovered sizzling hot plasma in the centers of galaxy clusters and in the diffuse space between galaxies. And they've let us make great strides in probing extraordinary black holes that lurk in the centers of all galaxies, ranging from a few million up to a few billion times the mass of the Sun. Their high energy relative to visible light means they're often created by events of unimaginable violence, phenomena unknown to us 50 years ago. That's the end of that section, and there's a little figure to show you guys. Let's see it. Oh, it's very small. Let me zoom in a little bit. So it's a little blurry, but it's just a thing to show you how, like, X-rays work. So there's this X-ray source, right? Like how a galaxy is an X-ray source. And these are kind of the illustration of X-rays. And if you have someone's hand in front of it, Some of those X-rays are going to be blocked by specifically like bone material, but it can pass through skin. So that's why you get, the film in the camera is going to show you bones. Whereas a galaxy can, as an X-ray source, the X-rays can go straight through gas clouds in between the galaxy and the Chandra telescope, which we're going to talk about later, and be received. So we can look at galaxies despite having some like visible light blocking material between them, which is pretty cool. All right. X-rays in popular culture. News of Roentgen's discovery of X-rays rippled around the world. When Roentgen discovered X-rays in November of 1895 by placing his hands between a Crookes tube and a fluorescent screen, the medical applications of the technology were immediately apparent. End quote. I wonder who that quote was by, because they didn't say it. Anyway, by January 1896, Roentgen had issued a report regarding his experiments to media in Europe and the United States. The public was immediately fascinated by the possibility of seeing through seemingly solid objects or inside the human body, and the topic made headlines in newspapers and weeklies. Apparently, hit my screen there for a second. Apparently, X-ray mania swept through the public sphere, but at a level far surpassing a simple cultural fad, explains Nancy Knight, who notes that, quote, X-rays appeared in advertising, songs, and cartoons, end quote. John Leanhart simply reports, quote, seldom has anything taken hold of the public imagination so powerfully and completely. Right away, magazine cartoons celebrated the idea. A typical one showed a man using an X-ray viewer to see through a lady's hat at the theater, end quote. Edwin Gerson had investigated the speed with which X-rays were incorporated into the branding of products in the United States, and he explores why so many marketers use the term X-ray to appeal to customers. Being a medical doctor, Gerson began collecting household products dating back to the 1890s, none of which had anything whatsoever to do with X-rays. One could purchase Sneitman's X-ray Liminant for horses and cattle, and Pat's X-ray Liminant for people. X-ray golf balls, ostensibly to improve the accuracy of one's game, were sold by John Wanamaker of New York. There was the D-cell X-ray flashlight battery, X-ray stove polish, X-ray cream furniture polish, manufactured in New York, and X-ray soap made in Port Huron, Michigan. X-ray blue double-edge razor blades were touted as, quote, the finest blades known to science, end quote. While drinking fountains for chicken houses were marketed by the X-Ray Incubator Company in Wayne, Nebraska. Housewives could purchase an X-Ray coffee grinder or the X-Ray lemon squeezer, and the X-Ray raisin seeder was available as early as November 1896. A company from Baltimore, Maryland sold boxes of X-Ray headache tablets with 8 pills for 10 cents, promising relief in just 15 minutes. Clearly, advertising by means of non sequitur is not just a phenomenon of the modern age. The popular fascination with X-rays continued for decades. By 1924, an X-ray shoe fitter was deployed by shoe vendors to image both feet inside a new pair of shoes. David Lapp reports that in the United States, quote, there were approximately 10,000 of these fluoroscopes in use, being made by companies such as Adrian X-ray Shoe Fitter, end quote, and that by the early 1950s, most shoe stores were using the devices. As Gerson points out, quote, the public was simply astonished with X-rays, and advertisers played off this spellbound attention by adding the name to almost any type of product. Not only did the image of the X-ray convey a sense of cutting-edge technology, it also functioned as a metaphor for powerful unseen truth and strength, end quote. Researchers and medical personnel working with X-rays were frequently exposed to dangerous or fatal levels of radiation, including Elizabeth Fleischmann, who at age 28 read a news article on how to build an X-ray device, and by 1900 became the best medical radiologist in the United States. But in 10 years' time, Fleischmann had been so badly overexposed to radiation by imaging her patients and developing the films that she did not survive. At the time, the effect of exposure to radiation was poorly understood, and this ignorance played out in dangerous exposure for both medical practitioners and those working with the new technology for purposes of entertainment. Nancy Knight, for instance, indicates that, quote, papers reported daily on Thomas Edison's efforts to X-ray a person's brain in order to figure out how the brain functions. Alan Grove reports that some speculated at the time the new technology might afford a kind of X-ray vision that might make it possible to capture on film the images of ghosts, apparently a popular notion in England. He also comments that within months of Roentgen's announcement, theaters were headlining performances inspired by the popularity of X-rays. Piano sheet music for American composer Harry L. Tyler's X-ray Waltzes from 1896 depicted on its cover a man holding his hand under an X-ray tube. Beneath the man's hand appears a skeletal X-ray image. In fact, in 2010, Tyler's waltzes were dusted off and featured in a BBC broadcast titled Images That Changed the World. And any discussion of X-rays in popular culture must recall that in the 1930s, when writer Jerry Siegel and artist Joe Shuster invented the prototypical superhero, it was inevitable that Superman would be gifted with X-ray vision. Though Superman didn't have such an ability at the outset, in later adventures he is able to see in multiple wavelengths of the electromagnetic spectrum, including radio waves, infrared, ultraviolet, and eventually X-rays. Roentgen's discovery had a deep shaping effect on the arts. This was because X-rays were an entree into a hidden world, the world within the world, represented by the interior structure of atoms and molecules. In 1912, less than 20 years after the initial discovery, physicist Max von Laue showed that X-rays were a form of electromagnetic radiation because they diffracted when interacting with matter. A year later, the father and son team of William Henry and William Lawrence Bragg described mathematically how X-rays scattered within a crystal, winning the Nobel Prize in Physics for their work in 1915. This opened the door to X-ray crystallography, a powerful tool for measuring the spacing and arrangement of atoms within a solid. The impact of this discovery was particularly strong in the visual arts, which were undergoing their own revolution with the onset of Fauvism, Cubism, and Futurism. The X-ray was liberating because to artists it proved that the external is not valid, it's just a false layer. Art historian Linda Dalrymple Henderson contends that X-ray suggests the possibility of stepping into the fourth dimension. She writes, quote, From the 1880s to the 1920s, popular fascination with an invisible, higher dimension of space, of which our familiar world might only be a section or shadow, is readily apparent in the vast number of articles and the books published on the topic. End quote. Henderson has demonstrated that modern artists readily embraced X-rays, and their ability to expose realities and perspectives not perceptible to the human eye as suggestive of four-dimensional space. Cubist paintings, with their simultaneous depiction of all sides of a seemingly transparent object, and their suggestion of interior planes, explains Henderson, quote, are testaments to the new paradigm of reality ushered in by the discovery of X-rays and interest in the fourth dimension. Such paintings are new kinds of windows, in this case, into the complex, invisible reality or higher dimensional world as imagined by the artist. End quote. The inspiration was sometimes very direct. According to historian Arthur Miller, Picasso's standing female nude was inspired by the power of X-rays to glimpse beyond the visible. What you see is not what you get. In this case, the inspiration was X-ray photographs taken to diagnose the illness of Picasso's mistress, Ferdinand Olivier. Superposed on a background of planes, her body lies open to reveal pelvic hip bones made of a geometrical shape, forms reduced to geometry, the aesthetic of cubism inspired by modern science. From the arts to medicine, and particularly through astronomy and space exploration, X-rays have profoundly altered human culture. That's the end of that section. I thought there was something that I was going to show you guys, but there's not. Just kidding. We're going to just keep going. I was like, oh, it's time to pause and show them a figure. There's no figure yet. I hope everyone's doing good on this Monday morning. Did you guys do anything fun this weekend? I just worked. So, nothing too crazy over here, but I'd love to hear if you guys did something fun. A gentle astrophysical giant. In 1923, Wilhelm Röntgen died as one of the most celebrated physicists of his time. A modest man, he had declined to take out a patent on his discovery, wanting X-rays to be used for the benefit of humankind. He also refused to name them after himself, and donated the money he won from his Nobel Prize to his university. That same year, Subramanian Chandrasekhar started high school in a small town in southern India. Chandra, as he was universally known, would grow into another great but modest scientific figure. Chandra means moon or luminous in Sanskrit. He was one of 9 children, and although his family had modest means, they valued education. Therefore, he was homeschooled, since local public schools were inferior, and his parents couldn't afford a private school. His family hoped Chandra would follow his father into government service, but he was inspired by science, and his mother supported his goal. In addition, he had a notable role model in his uncle, C.U. Raman, who went on to win the Nobel Prize in Physics in 1930 for the discovery of resonant scattering of light by molecules. Chandra's family moved to Madras, and he started at the university there, but he was offered a scholarship to study at the University of Cambridge in England, which he accepted. He would never live in India again. At Cambridge, he studied and held his own with some of the great scholars of the day. As a young man, he fell into a controversy with Arthur Eddington, at the time the foremost stellar theorist in the... Sorry, I had to yawn there. A controversy with Arthur Eddington, at the time the most foremost stellar theorist in the world, which upset him greatly. Eddington refused to accept Chandra's calculations on how a star might continue to collapse when it had no nuclear reactions to keep it puffed up. Chandra was a gentle man, unfailingly polite and courteous. In part due to this conflict, he chose to accept a position at the University of Chicago, where he spent the bulk of his career. His name is associated with the Chandrasekhar limit, the theoretical upper bound on the mass of a white dwarf star, or about 1.4 times the sun's mass. Above this limit, the force of gravity overcomes all resistance due to inner particle forces, and a stellar corpse will collapse into an extraordinarily dark object, either a neutron star, or, if there's enough mass, a black hole. In the 1970s, he spent several years developing the detailed theory of black holes. Chandra was amazingly productive and diverse in his scientific interests. He wrote more than 400 research papers and 10 books, each on a different topic in astrophysics. For 19 years, he was the editor-in-chief of the Astrophysical Journal, guiding it from a modest local publication to the international flagship journal in astronomy. He mentored more than 50 graduate students while at the University of Chicago, many of whom went on to be the leaders in their fields. In 1983, he was honored with the Nobel Prize in Physics for his work on the theory of stellar structure and evolution. Through his long career, Chandra watched the infant field of X-ray astronomy mature. The telescopes flown in sounding rockets in the early 1960s were no bigger than Galileo's spyglass. Sorry. Just before its 1999 launch, NASA's Advanced X-ray Astrophysical Facility was renamed the Chandra X-ray Observatory, CXO, in honor of this giant of 20th century astrophysics. In a span of less than 4 decades, Chandra improved on the sensitivity of the early sounding rockets by a factor of 100 million. The same sensitivity gain for optical telescopes, from Galileo's best device to the Hubble Space Telescope, took 400 years, or 10 times longer. Crazy stuff. I forgot my water today, so I'm just like, we get to the end of a section, and I'm like, okay, where's my water? Oh, there's nothing for me to grab. Right, I guess I'll keep going. All right. The Chandra X-ray Observatory. Until the Chandra X-ray Observatory was launched, the best X-ray telescopes were only as capable as Galileo's best optical telescope, with limited collecting area and very poor angular resolution. With Chandra, X-ray astronomers gained several orders of magnitude of sensitivity, and the ability to make images as sharp as a medium-sized optical telescope. Chandra was the third of NASA's 4 great observatories. The others are the Hubble Space Telescope, launched in 1990, and still doing frontier science, the Compton Gamma Ray Observatory, launched in 1991 and deorbited in 2000 after a successful mission, and the Spitzer Space Telescope, launched in 2003 and currently in the final warm phase of its mission, since its liquid helium coolant ran out in 2009. It took a while to open the X-ray window on the universe, because the Earth's atmosphere is completely opaque to X-rays. In the 1920s, scientists first proposed using versions of Robert Goddard's rocket to explore the upper atmosphere and peer into space. However, this idea wasn't realized until 1948, when a repurposed V-2 rocket was used to detect X-rays from the sun. The next few decades saw the development of imaging capabilities for X-rays and new detector technologies. And X-ray astronomy tracked the maturation of the space program. The first X-ray source beyond the solar system, Scorpius X1, in the constellation of Scorpius, was detected by physicist Riccardo Giacconi in 1962. This intense source of high-energy radiation is a neutron star, the end result of the evolution of a massive star where gravity crushes the remnant to a state as dense as nuclear matter. The intense X-rays result from gas being drawn onto the neutron star from a companion and being heated violently enough to emit high-energy radiation. Giacconi is another giant in astrophysics. As leading scientist for X-ray observatories from Uhuru in the 1970s to Chandra in the 1990s, first director of the Space Telescope Science Institute, and winner of the Nobel Prize in Physics in 2002. This last and ultimate accolade fittingly came almost exactly a century after the award of the first Nobel Prize in Physics for the discovery of X-rays to Wilhelm Röntgen. Born in Genoa, Italy, his early life was disrupted by the Second World War. As a high school student, he had to leave Milan during Allied bombing raids. He returned to complete his degree and start his life as a scientist in the lab, working on nuclear reactions in cloud chambers. With a Fulbright Fellowship, he moved to the United States and forged his career there. He had his hand in all the pivotal discoveries of X-ray astronomy, the identification of the first X-ray sources, characterization of black holes and close binary systems, the high energy emission that emerges from the heart of some galaxies, and the nature of the diffuse X-rays that seem to come from all directions in the sky. The growth in the number of celestial X-ray sources gives a sense of how each new mission has advanced the capabilities. 160 sources in the final catalog of the Uhuru satellite in 1974, 840 in the HEAO A-1 catalog in 1984, nearly 8,000 from the combined Einstein and ExoSat catalogs of 1990, and about 220,000 from the ROSAT catalog of 2000. Chandra has had a wider field but lower sensitivity counterpart in the European XMM-Newton mission, also launched in 1999. These two X-ray satellites have detected a total of over 1 million X-ray sources. Chandra was launched by the Space Shuttle Columbia into a highly elliptical orbit that takes it a third of the way to the moon. At 5 tons, it was the most massive payload launched up to that time by the Space Shuttle. The elongated orbit gives it lots of hang time in the perfect vacuum of deep space, and lets science be done for 55 hours of the 64-hour orbit. This comes at the expense of the spacecraft being unserviceable by the shuttle when it was still flying, so the facility has to work perfectly. In fact, the only technical problem was soon after launch when the imaging camera suffered radiation hits during passage through the Van Allen radiation belts. It is now stowed as the spacecraft passes through those regions. The spacecraft has a nominal 5-year mission at time of launch, but it's producing good science well into its second decade and is expected to last at least 15 years. One of the two different imaging instruments can be the target of incoming X-rays at any given time. The high-resolution camera uses a vacuum and a strong electric field to convert each X-ray into an electron, and then amplify each one into a cloud of electrons. The camera can make measurements as quickly as 100,000 times per second, allowing it to detect flares or monitor rapid variations. Chandra's workhorse instrument is the Advanced Camera for Imaging Spectroscopy. With 10 CCDs, it has 100 times better imaging capability than any previous X-ray instrument. Either of these cameras can have one of two gratings inserted in front of it it can have one of two gratings inserted in front of it to enable high and low resolution spectroscopy. Spectroscopy at X-ray wavelengths is a bit different from optical spectroscopy. The spectral lines seen by Chandra are usually very high excitation lines of heavy elements, like neon and iron, coming from gas that's kept highly agitated by high-energy radiation or violent atomic collisions. There are three major differences between optical and X-ray detection of sources in the sky. The first is the way the radiation is gathered. X-rays falling directly on silvered glass have such high energy that they penetrate the surface and are absorbed, like tiny bullets. X-ray telescopes use a shallow angle of incidence, so that the photons bounce off the mirror like a stone skimming off water. Chandra uses a set of 4 concentric mirrors, 6 feet long and very slightly tapered, so they almost look like nested cylinders. This method of gathering radiation makes it difficult to achieve a large collecting area. The second difference is the much higher energy of X-rays. Chandra measures photons in a range of energy from 0.1 to 10 keV, or 100 to 100,000 electron volts. 100 to 10,000 electron volts, which is a standard unit of measure for photons. On the electron volt energy scale, two numbers that bracket this range are 13.6 eV, the modest energy required to liberate an electron from a hydrogen atom, and 511 keV, the rest mass energy of an electron. For reference, photons of visible light have wavelengths 10,000 times longer and energies 10,000 times lower. With each photon packing such a punch, a typical astronomical source emits far fewer X-ray photons than visible photons, so each is very valuable. The goal in X-ray astronomy is to detect every photon individually. Very few photons are required to detect a source, and this is helped by the fact that the background rate is slow. X-rays are not created by miscellaneous or competing sources, so the X-ray sky is sparsely populated. In some of the deepest observations made by Chandra, 2 or 3 photons collected over a 2-week period is enough evidence to declare that a source has been detected. There are papers in the research literature with more authors than photons. Chandra unlocks the violent universe because celestial X-rays have high energy and can only be produced by extreme physical processes. The sun and all normal stars are very weak X-ray sources because their cool outer regions produce thermal radiation peaking at visible wavelengths. It would take a gas at hundreds of thousands or millions of degrees to emit copious X-rays. Diffuse gas with this very high temperature is distributed between galaxies. Another way X-rays can be made is when particles are accelerated to extremely high energies. They release the energy in a smooth spectrum that extends to X-rays and even gamma rays. Despite the million-plus X-ray sources that have been cataloged, there are thousands of times more optical sources, so the X-ray sky is relatively quiet. But many of those X-ray sources are extremely interesting because they're situations where matter has been subject to extreme violence. That's the end of that section. Let's see, how long is this chapter? I checked this before, but then I promptly forgot. It's pretty long. Okay. Well, then I guess we'll just keep going. Heart of darkness. Black holes are black. That seems like a self-evident statement. Nothing can escape the event horizon of a black hole. The event horizon isn't a physical barrier or a boundary, but an information membrane, defining the region from which no particle or radiation can escape. Black holes are the ultimate expressions of general relativity, where mass curves space so much that a region is pinched off from view. Black holes are the final states of massive stars. Every star is in a lifelong battle between the forces of light and darkness. The light comes from fusion reactions, creating pressure that pushes outward, while the dark is the implacable force of gravity pulling inward. In the end, gravity always wins. When a star 20 or more times the sun's mass exhausts its nuclear fuel, the core collapses into a state so dense that nothing can escape, not even light. An isolated black hole would be black and undetectable. However, more than half of all stars are in binary or multiple systems. And that's also true of the most massive stars that collapse catastrophically when their nuclear fuel is exhausted, forming a black hole. The rotation of the star is amplified in its newly compact state, so the black hole spins very fast. As material from a companion star is pulled onto the black hole, it forms a disk of gas, like water swirling into the drain of a bathtub. The disk is very hot, tens of thousands of degrees, and it glows in ultraviolet radiation and X-rays. Some hot plasma is accelerated along the pole of the spinning black hole, where it emits X-rays and gamma rays. So while a black hole is black, gas from a companion can be heated into pyrotechnic activity when it's falling into the black hole. The accretion process is well enough understood, theoretically, that X-ray signatures can be used to identify black holes. Some of the radiation comes from no more than 100 kilometers from the event horizon. The Chandra Observatory has played a vital role in this work. And I have a figure for you guys. Let's check it out. Hold on. There it is. So this is an image of a binary star system where one star is a black hole, and it's just kind of illustrating how we detect black holes using X-rays. So obviously the black hole itself is just black, right? We can't see it, but when a black hole is close enough to its companion star that it like sucks the energy away, you can see these high energy X-rays, and this is kind of like a wavelength illustration of these X-rays. So that is how we detect black holes. Artists do add so much to our understanding of a theory or concept. That's, yes. It's a really great way to illustrate things. All right. Also, hello, Ox Bowman and Student McLeod, and welcome to chat. Chandra has the sensitivity to detect stellar black holes hundreds of light years away. Only about 20 binary systems have well enough measured masses to be sure the dark companion is a black hole. But X-ray observations can be used to identify black holes with fairly high reliability. The examples studied with X-ray telescopes are the brightest representatives of a population of about 100 million black holes in the Milky Way. X-ray observations have also pushed the limit of our understanding of black holes. In 2007, a research team used Chandra to discover a black hole in M33, a nearby spiral galaxy. The black hole was 16 times the mass of the Sun, making it the most massive stellar black hole known. Moreover, it was in a binary orbit with a huge star 70 times the Sun's mass. The formation mechanism of the black hole that placed it in is such a tight embrace with its companion is unknown. This is the first black hole in a binary system that shows eclipses, which provides unusually accurate measurements of mass and other properties. The massive companion will also die as a black hole, so future astronomers will be able to gaze on a binary black hole where energy is lost as gravitational radiation and the two black holes dance a death spiral as they coalesce into a single beast. That's the end of that section. But like I said before, I'm just going to keep going. Stellar cataclysm. The formation of a black hole is just one half of the story when a massive star dies. As the star reaches the end of its life, and all fusion energy sources are exhausted. It suffers a dramatic gravitational collapse. The crushing force of infalling gas squeezes the core into a black hole, but much of the mass rebounds outward, and the outflowing gas meets more infalling gas and heats it momentarily to billions of degrees. Heavy elements like gold and silver and platinum are created in that thermonuclear blast, and they surf into space to become part of future generations of stars. This is a supernova. For centuries and millennia after the supernova event, outrushing gas interacts with the interstellar medium to form a delicate filigree of nebulosity and filaments of glowing gas. Supernova remnants are most clearly seen in X-rays, and with Chandra, their structure can be studied in great detail. The spectrometers on Chandra have mapped the ejection of iron and silicon, and oxygen and nitrogen, elements essential for planet building and for life. Cosmic alchemy is part of our story, since every carbon and oxygen atom in every person was once part of a previous generation of stars. The imagers on Chandra have observed the shock-heated filaments in enough detail to model the process that accelerates particles to within a fraction of a percent of the speed of light. Chandra has observed supernova remnants at different stages of their evolution and used them to piece together the expansion history of a typical dying star. This research has an intriguing connection to human history. Tycho's supernova of 1572 in the constellation of Cassiopeia and the Crab Nebula supernova of 1054 in the constellation of Taurus were two of the brightest guest stars of the last millennium, visible to the naked eye and in the historical record of many cultures. Recently, Chandra data led to a revised age for the supernova remnant RCW86, and the detonation date of AD 185 perfectly matches the notation of a guest star in records of the Chinese court astronomers, making this the first supernova in recorded human history. At the center of a supernova remnant is either a black hole or a neutron star. Neutron stars aren't as exotic as black holes, but they are quite bizarre. The pressure of gravity forces protons to merge with electrons and create pure neutron material. Without the electrical repulsion to keep the particles separate, they are as close together as marbles in a jar. A neutron star is like a giant atomic nucleus with an atomic number of 10 to the 57. Chandra can see neutron stars via the high-energy phenomena spawned by their intense magnetic fields. A neutron star has a magnetic field of about 10 to the 12th Gauss, equivalent to 10 billion refrigerator magnets. They are spinning at typical speeds of 60 RPM, and sometimes as quickly as 45,000 RPM. Imagine something 1,000,000 times the mass of the Earth, that's the size of a city, and spinning nearly 1,000 times a second. Chandra images of dozens of neutron stars have revealed glowing clouds of magnetized particles blowing away from the neutron star like a wind. That's the end of that section. How's everyone doing today? I gotta crack my neck. Hold on. Oh, it didn't crack. For anyone keeping track. I do a little stretch. I hope everyone's doing good today. Can we use a super telescope using an Einstein ring produced by a black hole? I don't know. Interesting question. I'm checking to make sure I understand fully what an Einstein ring is. Yes, it's from the, what's it called? Gravitational lensing. I mean, like, gravitational lensing in itself is how we can, like, see kind of deeper into space. Or well, maybe not deeper into space, but we can see things, see objects that we might not normally see. I don't know about, like, that's kind of more of a question for Professor Impey, I would say, because that's very, like, a very theoretical kind of thing. I don't know too much about the theories of, like, future telescope technology. I guess it's possible. I mean, we kind of use Einstein rings already in like gravitational lensing as like temporary telescopes kind of thing. If you know what I mean. To see stuff, you know? We use gravitational lensing to see stuff. But, and we do see distant objects using gravitational lensing, but I don't know about like building a super telescope with an Einstein ring or something like that. I'm not sure. Sounds interesting though. All is well in Charlotte. I'm glad. All is well here in LA as well. It's been like cloudy lately actually, which is weird. It's normally not cloudy here. All right. Black holes. From speculation to observation. In 1964, Riccardo Giacconi and his team discovered Cygnus X1, a source in the constellation known as the Swan that is generally accepted as the first black hole detected. Cygnus X1 has a mass 9 times that of the Sun, with an implied event horizon size of 16 miles, smaller than a city. But in the early 1960s, X-ray astronomy was an emerging science, and a singularity was then considered purely theoretical. Science writer Dennis Overby recounts how physicist John Wheeler, based on his studies' prompting, eventually came to accept the probabilities of the cataclysmic collapse of a star. Quote, in 1939, J. Robert Oppenheimer, who would later be a leader in the Manhattan Project, and a student, Hartland Snyder, suggested that Einstein's equations had made an apocalyptic prediction. A dead star of sufficient mass could collapse into a heap so dense that light could not even escape it. The star would collapse forever, while space-time wrapped around it like a dark cloak. At the center, space would be infinitely curved, and matter infinitely dense, an apparent absurdity known as a singularity. Dr. Wheeler first... The leaf blowers have returned. Dr. Wheeler at first resisted this conclusion, leading to a confrontation with Dr. Oppenheimer at a conference in Belgium in 1958, in which Dr. Wheeler said that the collapse theory does not give an acceptable answer to the fate of matter in such a star. End quote. Saw some people in chat. Do you think an accretion disk around the black hole could be the light source? Yeah, without an accretion disk, there would be no light source to... Yeah. Yeah, I'm a little confused by the concept. I think Remus is trying to get at something with gravitational lensing. But I'm not quite sure. Oh, there's a little article about this. Interesting. I mean, I suppose it's possible. Yeah, not a raw black hole though. Yeah, we would have to. I think this article that you sent suggests like it says if we use the sun as a gravitational lens telescope, which makes sense because the sun does have like like you need a, as student McLeod said, you need some sort of like light source, which is why we use like binary systems and stuff. But yeah, I'm not sure. Again, probably something that Professor Impey can answer in a more succinct way than what I can do. Regular disclaimer, I'm the Twitch and video expert of the team, and a not a degreed astronomer, just a someone around to learn. A black hole does have a huge mass, but that's why you need it in a binary system in order to do any of the gravitational lensing, or else you don't have any accretion disk to see things with, I believe. All right. However, By 1967, during a presentation in New York, Wheeler had reconsidered and, quote, seizing on a suggestion shouted from the audience, hit on the name black hole to dramatize this dire possibility for a star and for physics, end quote. Mitchell Begelman and Martin Rees likewise noted that it was Wheeler who first officially used the term black hole in reference to a collapsed star, and comment that the name immediately caught on. They write, quote, here was something infinitely more mysterious, and perhaps much more sinister as well. A place where any form of matter or energy could enter, lose its identity, and be lost forever to the universe. End quote. In Black Holes and Time Warps, Caltech astrophysicist Kip Thorne similarly observes, quote, of all the conceptions of the human mind, from unicorns to gargoyles to the hydrogen bomb, the most fantastic, perhaps, is the black hole. A hole with a gravitational force so strong that even light is caught and held in its grip. A hole that curves space and warps time. End quote. In 1970, Stephen Hawking developed theorems that demonstrated black holes would be a standard phenomenon of Einstein's general relativity and of the universe. By the mid-1970s, not surprisingly, black holes were resonating across the realms of fiction, popular music, art, and film. The Canadian rock group Rush released Cygnus X1, Book 1, The Voyage, on their album A Farewell to Kings. It's an extended rock composition written in homage to the X-ray emission source that Riccardo Giacconi discovered in Cygnus. The lyrics read in part, in the constellation of Cygnus, there lurks a mysterious invisible force, the black hole of Cygnus X1. Invisible to the telescopic eye, infinity, the star that would not die. All who dare to cross her course are swallowed by a fearsome force. I sent a course just east of Lyra and northwest of Pegasus, flew into the light of Deneb, sailed across the Milky Way. The X-ray is her siren song. My ship cannot resist her long. Nearer to my deadly goal until the black hole gains control. Sound and fury drowns my heart. Every nerve is torn apart. Located approximately 6,000 light-years from Earth, Cygnus X1 is now thought to be a high-mass X-ray binary system in which gaseous material from the blue supergiant star HDE 226868 is accreting onto a nearby black hole created by the collapse of a star 9 times the mass of our Sun. The system emits powerful X-ray radiation as gas from the blue supergiant siphons onto and is heated by the black hole. Interest in Cygnus X1 was further sparked by a public and congenial bet between Stephen Hawking and Kip Thorne regarding the physics of the object. By 1990, having argued that Cygnus X1 was not a black hole, Hawking admitted to losing the wager. And that's the end of that section. Yeah, as Student McLeod said, an Einstein ring is like lensed light. Mass isn't lensed. So, despite it having a large mass, it needs the light in order to make the ring, essentially. That's why we only look for black holes where we can only find black holes where there are like binary stars. Because you can't see it. Unless there's something that's accreting around it. All right. Science in the matrix of culture. No longer the stuff of science fiction, black holes pervade all facets of culture. Wallace and Karen Tucker, in recounting the history of the Chandra X-ray Observatory, note that the telescope has offered, quote, substantial observational evidence for the existence of black holes, which they claim have since, quote, become a part of popular literature as a metaphor for an irretrievable loss of material, time, money, and so on, end quote. In the hands of English novelist Martin Amis in Night Train, black holes became a metaphor for death. But black holes are understood in the public arena as far more substantial than a mere metaphor. In 2008, it was reported that physicists at CERN's Large Hadron Collider could produce miniature black holes that in a runaway scenario might swallow the Earth. In fact, Public concern over the possibility of scientists manufacturing microscopic black holes led to the facility posting an information and safety webpage that reassures general audiences of the following. Quote, speculations about microscopic black holes at the LHC refer to particles produced in the collisions of pairs of protons, each of which has energy comparable to that of a mosquito in flight. Astronomical black holes are much heavier than anything that could be produced at the LHC. According to the well-established properties of gravity, described by Einstein's relativity, it is impossible for microscopic black holes to be produced at the LHC. There are, however, some speculative theories that predict the production of such particles at the LHC. All these theories predict that these particles would disintegrate immediately. Black holes, therefore, would have no time to start accreting matter and to cause macroscopic effects. End quote. Any of you guys remember that? I distinctly remember that. I was in middle school at the time, so maybe that's showing how young I am. But in 2008, I was in middle school, and I distinctly remember going on the bus one day, and all my friends were talking about how we were all gonna die because this place was making black holes somewhere on the other side of the world, and I was so scared, and then went to school and got distracted and forgot about it. But I don't know, do you guys remember that? I was young, so I did not know what was going on. A year later, J.J. Abrams' film Star Trek, from 2009, depicted Romulans generating, at will, miniature black holes that could devour starships and planets. Actually, Star Trek and black holes have a history that goes back to the same year Wheeler started using the term. The idea of a collapsed or black star was floated in the first season of the original Star Trek series in an episode titled Tomorrow is Yesterday, first aired in January 1967, in which the Starship Enterprise encounters a black star of high gravitational attraction. As Captain Kirk and the crew attempt to escape its gravity well, their ship is slung into a time warp that sends them plunging back through time. The Enterprise ends up adrift in Earth orbit in 1968, just days prior to the first manned moon mission. Though not referred to as a black hole, the black star that triggers their adventure was the product of Einstein's singularity and Oppenheimer and Snyder's collapse star. From space artists like David A. Hardy to amateur astronomers like Stephen Cullen, many have speculated what Cygnus X1 might actually look like. Hardy's rendering depicts powerful X-ray jets shooting from the poles of the binary system's black hole. Cullen actually photographed those jets in May 2009. Quote, luckily, Cygnus X1 inhabits a region of space thick with gas that emits specific kinds of radiation when hit by shock waves, energetic particles, and relativistic jets from black holes, end quote, writes Cullen, who notes that astronomer David Russell and a team working with him had already obtained, quote, visual evidence of a jet-powered nebula caused by the northern jet slamming into the interstellar medium, end quote. But Cullen thought there might be a powerful jet emerging from the southern pole, and there was. Quote, unlike the northern region, the images did not show a well-defined shell of shocked gas, he recalls. What I did see, however, was a diffuse, fan-shaped glow that traced a path directly back to Cygnus X1, end quote. Having obtained clear images of the previously undetected jet, Cullen subsequently invited Russell's comments, and together the astronomers collaborated to publish Cullen's results. The discovery demonstrates the extent to which the Chandra Observatory has prepared astronomers to anticipate what might be explored in wavelengths beyond visible light. Not only have Chandra's X-ray observations demonstrated profound effects, Not only have Chandra's X-ray observations demonstrated profound aspects of the high-energy universe otherwise unavailable to telescopes, but its images have opened the universe for visually impaired readers as well. In 2007, astronomy educator Noreen Grice and astronomers Doris Dow and Simon Steele published Touch the Invisible Sky, in which Braille text and especially prepared Braille images detailed discoveries by Chandra, Spitzer, and other telescopes that reveal the universe in electromagnetic wavelengths not visible to the human eye. In that text and other NASA Braille books, Readers can experience the infrared, ultraviolet, and X-ray universe through their fingertips. The popular fascination with black holes seems hinged on the fact that a singularity and its event horizon contort our wildest imaginings about the physical universe. We think we can wrap our minds around just about any natural phenomena, but black holes defy all logic at the point of the singularity and leave unanswered questions regarding the physics at its core. Kip Thorne asserts that black holes have much to tell us about the birth and the future of the universe. Quote, gravitational wave detectors will soon bring us observational maps of black holes, and the symphonic sounds of black holes colliding. Symphonies filled with rich, new information about how warped space-time behaves when wildly vibrating. Supercomputer simulations will attempt to replicate the symphonies and tell us what they mean. And black holes thereby will become objects of detailed experimental scrutiny. End quote. Like the music of the universe discussed in the chapter on WMAP, the universe has more to tell us in the narratives or symphonies we are yet to learn from black holes. One thing at least seems certain. The new understandings of massive black holes that Chandra is unfolding will inevitably be woven into the matrices of human culture and language, poetry and music, and even our dreams. That's the end of that section. Let's see how much more we got. All right, about a little less than 10 more pages. All right. The enigmatic center of our galaxy. 20 years ago, evidence began to accumulate that the center of the Milky Way galaxy contained a dark mass that could not be accounted for as a normal stellar remnant. Star motions in the center were so rapid they indicated a huge black hole, about 4 million times the mass of the Sun. The evidence for this supermassive black hole is now better than for the more conventional black holes that result from the death of a massive star. The mass is not just based on stellar velocities, but on tracking the entire stellar orbits as they loop around the central dark object. Chandra did not contribute the evidence that cemented the case for a large black hole in the galactic center, but it showed that the black hole was unusually anemic, emitting far less high-energy radiation than other massive black holes. Even as it devours 10 to the 19 kilograms of material each second, it radiates energy 1 million times less efficiently than a set of stars of equivalent mass. Yet, while the black hole in the galactic center is very feeble, it's not boring. 10 years ago, an X-ray flare was seen coming from the vicinity of the black hole, and since then, hundreds of flares have been seen, occurring almost daily. They've raised the level of X-ray emission tens or hundreds of times above the quiescent state. Such rapid flares must be created within 10 times the event horizon scale, close to the point of no return. The galactic center also harbors a source of energy intense enough to create antimatter in the form of positrons. The real mystery is the inactivity of the galactic center. The center of our galaxy harbors a massive star cluster with star densities thousands of times higher than those seen in the solar neighborhood, and there is plenty of gas available within 10 to 20 light years. So why is the black hole so quiet? The best guess is that it's currently starved, because explosive events have cleared away much of the gas from around it. Chandra has provided evidence for this explanation. There are lobes of X-ray emission that indicate the black hole was more active 5,000 or so years ago, and blobs of plasma emerging from the center argue for quasi-periodic activity. Remarkable observations Remarkable observations from a few years ago saw a cloud of gas near the black hole brighten and fade in only a few years, responding to an X-ray pulse that had traveled for 300 years to get there. We can infer that the black hole was 1 million times brighter 300 years ago, when Queen Anne had just ascended to the throne in England, and the largest town in her American colonies was Boston, with a population of 7,000. However, the galactic center is about 27,000 light years from Earth, so all of this action really happened in the late Stone Age, before humans settled down into civilizations, and the information is just reaching us now. And that's the end of that section, and I have a picture for you of Sagittarius A. There it is. So this isn't the direct picture from the book, but it's a nice picture of Sagittarius A star in X-ray. This is I do not know why this is circled, but we're looking here. So SGR A star right there. That's right around where the black hole is. Black holes are so cool. They're wild. Sorry, I had to yawn again. Yeah, they're strange little things. Suppose our galaxy had enough time without other events. Is the tendency of all stars to enter the event horizons? I don't believe so. I don't think that because like event horizons, honestly, like for most black holes, they don't extend that far. And like the accretion disks don't extend that far. I think there was like a thing where it was like if the sun was a black hole, I don't believe it would disturb, like, I mean, it would change things, but like I don't think the gas giants would like end up in like falling into the event horizon or in the accretion disk, I think. But I might be wrong on that, don't quote me. But no, I think it's I think a lot of stars would just kind of hang out because while, you know, black holes are more common than like sometimes they seem, they're not that common. Like they're you need very big stars to turn into black holes. If the sun were a black hole, nothing about our orbits would change. Thank you. Yeah. So like you know, and that's just within a single solar system, you know. So a lot of it's really just the binary systems. It would just be very dark. Also, Highland Jersey, you working on your taxes? Oh, that sucks. I hope you were able to finish them. But what's it called? The reason that like some stars, you know, fall into these accretion disk around black holes is usually because they're just the binary star system, or like tertiary. Is that the word? Tertiary? Is it 3? It's tertiary. Triple star system. But if they're like partner stars, essentially, then one will feed into the other. But other stars are probably going to be fine. Fun side fact, the sun isn't big enough to become a black hole. Very true, yes. It is not at the, what's that limit called? Is that the Chandrasekhar limit? Or is that the Hawking limit or something? There are many different limits. But, yes, the sun is not large enough to become a black hole. It's just like a fun thing to theorize. Like, what would happen to our solar system if it was a black hole? A supernova would mess it up. So that's not a promise. But because there'd be no living creatures with eyes to see it, would it really be dark? Oh my god. Anyway, we will get back to this. Supermassive black holes. Oh, look, we get to talk more about them. Cockroaches would probably be fine for a while. All right. In the 1960s, long before the Milky Way was known to have a supermassive black hole, violent activity was seen in the centers of some distant galaxies. The manifestations were gas motions 100 times faster than what would be seen in a normal stellar system. Intense radio emission concentrated in a tiny region of the galactic nucleus, and radiation across the electromagnetic spectrum from radio waves to gamma rays. Some of the strongest X-ray sources in the sky are galaxies hundreds of millions of light years away, which means that they have an X-ray emission thousands of times stronger than a galaxy in the Milky Way. Rapid variability of the radio, optical, and X-ray emission localize the intense activity to regions light days across, only 10 times bigger than the solar system. No star cluster can pack so much radiation into such a small volume. The only plausible explanation was a gravitational engine, a black hole. Imagine a city like Los Angeles. That is easy for me to do. Viewed from high above in a helicopter, where every street light, every house light, and every car light is standing in for a star. There are probably 100 million lights in the greater Los Angeles area, so in this analogy, each light represents 1,000 stars. Los Angeles is like the disk of a spiral galaxy. Now imagine a light 1 inch across in the city center that emits 100 times more radiation than all the city lights put together. That's the intensity of an active galactic nucleus. It would be clearly visible from an immense height, long after the individual lights in the city had faded from view. We can see an incredibly bright point of light, but the surrounding galaxy is too faint to see. That's a quasar. Through the 1990s, astronomers realized that every galaxy contains a black hole, with a mass that scales with the mass of the old stars in the center of the galaxy. Moreover, these black holes are not active most of the time, so we're not feeding and spewing out the energy that makes them easy to detect. The Milky Way is a medium-sized galaxy, with a 4 million solar mass black hole that's currently inactive. The brightest quasars harbor black holes 1,000 times larger, or a few billion times the mass of the Sun. These extraordinary gravitational engines, form and grow quite naturally as galaxies form and grow, but steadily consume matter, and by occasional mergers. It's remarkable that nature makes black holes spanning a factor of 1 billion in mass, from a few times the mass of the Sun to the mass of a small galaxy. Their sizes range by the same factor of 1 billion, but they all share the properties of having an event horizon and, it is supposed, a central singularity. Strange as it might seem, massive black holes do not represent an extremely dense state of matter. The size of the event horizon is proportional to mass, but the volume increases by the cube of the size. So the more massive a black hole is, the less dense it is within the event horizon. The 3 billion solar mass beast at the heart of the elliptical galaxy M87 is not much denser than water. Modest density does not, however, reduce their intrinsic strangeness. And thank you so much for that follow. Was that LCSPB? Welcome to the TeachAstronomy family. What are you guys talking about in the... Somebody got 29 lashes? Cockroaches. What is the radius of a black hole with mass like the Sun? I don't think you can I don't think that's possible. Astronomy fans receive grace on Mondays, yes. You guys give me grace for changing times and canceling things and stuff, so you get it as well. Well, a star the mass of the Sun can't be a black hole, so those don't exist. But if you're saying, like, how much would it have to... What is the radius of a black hole with a mass like the Sun? Oh, I understand. How small would it be? It'd be very small. In comparison to the Sun, at least. It's probably something you type into Google if you know the right phrase. It's possible, but only if a larger black hole shrank in the wash. The jokes today. The jokes. I love it. Oh my god. Sun has a black hole? I don't know. What if our sun became a black hole? No, our sun will not turn into a black hole. Oh, it's the Schwarzschild radius. That's the limit I was looking for. I don't know off the top of my head. It'd be something I'd have to Google, and I don't really have too much time today to Google that. But it would be I feel like when they do these things, it's something like, it's the size of like a small state in the United States or something like that. Yeah, it's like Stephen McLeod said, you can Google around. I just like don't have the time to like find the right phrase because I gotta finish this chapter for you guys before I go to work. But let me know if you find it, Remus, because it's a fun theory, or not theory. It's a fun thing to like thought experiment to think about. Wouldn't it be a point source at best? I thought if our sun collapsed, it would be a neutron star, not a black hole. Yeah, there's definitely not enough mass. This is all like theoretical. There's no way, well, not even theoretical, because like black hole theory is different than, but like it's like a fun thing to think about. Like if this, like how dense would it have to be in order to become a black hole? It can't, but how much would it be? But yeah, I can't remember the answer either. It might be a point source. It might have to be that dense. I'm not positive. Oh, I have a figure for you too. I got distracted by the black hole talk. Where's my arrow? Oh my goodness. I would like to go to the next picture, please. Okay, hold on. Oh, it's because the next picture is not there. Hold on. We're gonna find it. It's in my email. Here we go. Okay. Here's a picture. I took it from the book, so apologies for the quality. But this is M87. And it says it's a giant elliptical galaxy with a supervolcano of X-ray activity originating from a black hole about 3 billion times the mass of the sun at its center. And the little Icelandic volcano is a fun little comparison to the X-ray and radio wave image of M87. So just a fun little thing. Yes, Stephen McLeod said a star with the mass of our sun will become an Earth-sized white dwarf, not a neutron star or a black hole, because it's too small. You can find, like, if you guys are interested in like those limits and stuff too, there's a bunch of stuff online that like explains like the Schwarzschild radius limitation stuff and how big a star has to be in order to become, you know, either a black hole, a neutron star, a white dwarf, all that jazz, a brown dwarf. You can theoretically have much smaller black holes. They just can't form naturally. Yeah. You guys know what's up. All right, I'm going to continue. Chandra has played a vital role in telling the story of supermassive black holes and their behavior. In nearby galaxies, it has detected vast bubble-like cavities and wave-like ripples in hot gas near the center, signs of blowback from the central engine. X-rays provide evidence of repetitive explosive activity, where mass falls onto the black hole, sparking it into activity and triggering jets of high-energy particles, which then evacuate the nearby volume and starve the black hole until the new material accumulates. In this way, a massive black hole can be inactive most of the time. Chandra has also seen binary black holes in the centers of merging galaxies. In one case, 2 huge black holes are only 3,000 light-years apart and will merge in the next 100 million years, provoking a cataclysm of gravity waves and new activity, and yielding a single galaxy with a larger black hole. This is direct evidence for the manner in which galaxies and their embedded black holes have grown by mergers and acquisitions over billions of years. Black holes and galaxies evolve on cosmic timescales of billions of years. So to figure out how they change the strategy is to make deep surveys that capture the census of active and inactive black holes at a range of distances or redshifts. The Chandra Deep Field was stared at for 2 million seconds, over 3 weeks, to develop the deepest X-ray image of the sky ever made. This deep field, covering a patch of sky smaller than a postage stamp held at arm's length, is combined with a shallower but wider survey to tell the full story. One of us, CDI, has participated in this research, with a survey of active galaxies in a 2 square degree region. Oh, I just realized when they said one of us, they meant one of the authors, and they meant Chris, Professor Impey. So Professor Impey has participated in this research with a survey of active galaxies in a 2 square degree region that netted more than 2,000 supermassive black holes and showed their evolution in cosmic time. This survey was sensitive enough to catch feeble accretors and black holes similar in size to the one in the Milky Way. The broad conclusion of these surveys is that star formation and black hole growth in a galaxy are tightly linked. The heaviest black holes, 100 million times the sun's mass or larger, ate voraciously in the first few billion years after the Big Bang, and have been grazing or fasting since then. Black holes 10 to 100 million times the sun's mass had a more well-regulated diet, and because they consume smaller proportions of their gas and dust early on, they continue to grow even today. X-rays are crucial to telling this story, since they can penetrate regions that would extinguish optical and ultraviolet radiation. The typical size of a galaxy forming a supermassive black hole of a particular mass reduces with cosmic time, so the biggest black holes formed first. Massive galaxies in the far-flung universe misspent their youths by building monstrous black holes. This result is apparently at odds with the hierarchical mode of formation of structure in the universe, where small objects form first and gradually grow into larger objects. This unexpected phenomenon has been called downsizing. A byproduct of this research is the solution to an old mystery of the X-ray sky. When the first X-ray satellites took their data in the 1960s and 1970s, they saw a faint diffuse glow that spanned the entire sky. This X-ray background was unexplained. Surveys with Chandra and the XMM Newton show that the background is actually composed of a myriad of pinpoints of X-ray emission from the active galaxies 3 to 8 billion light-years away. Also, a majority of the emission is from galaxies where the nuclear activity is shrouded by dust and would not have been visible to an optical telescope. These surveys have also shown that black holes in the most massive galaxies are green. By comparing the available fuel with the energy required to evacuate cavities in the central regions, the efficiency can be calculated. It's high because the mass is accreted slowly and smoothly, and the energy is extracted very close to the event horizon of the black hole. If a family car was as efficient as one of these supermassive black holes, it would get 1 billion miles to a gallon of gas. That's the end of that section. Looks like we've got just one more till the end of this chapter. This is hurting my head. Pardon the hair. The book Black Holes and Time Warps by Kip Thorne goes into a lot of detail and is super approachable for non-physicists. That sounds great. Thank you for that recommendation. Yeah, the Schwarzschild radius is at 2.954. So that's the point at which you can start getting... Is it black holes or is it neutron stars? Oh, there's a Schwarzschild radius calculator. That's fun. Nice. Thank you for that. I think it's, what's it called? Solar masses. Oh, it's Coulomb. What? I think it's solar masses. I'm not sure. Isn't that solar masses? For, I don't know if that's the... Hold on. I'm gonna look it up. How do you spell Schwarzschild? I don't want to give you guys wrong information. Can a human become a black hole? Apparently that was a question that Google wanted to make sure I knew the answer to. Oh, I see. I see what we're talking about. Mm-hmm. What am I looking at? Is there not just like a solar... Maybe I'm thinking of something else. I'm confused, clearly. I was thinking of like the limits of like how many solar masses until you can make a neutron star, how many solar masses until you can make a black hole. Why don't we change the units? That's a great question. I have no answer for you. It makes no sense. I realize this. But apparently, for Mimas's research, the sun would have to condense into 2.954 kilometers or 1.84 miles radius, I'm assuming. Diameter? Radius, I think. And then it would turn into a black hole. So very small. Thank you for looking that up. That's very interesting. And I'm going to finish this out. All right. Hunting dark matter and dark energy. Chandra has also weighed in on two of the profound mysteries of cosmology: the nature of dark matter and dark energy. These two components of the universe account for 95% of its behavior, yet the physical basis for them is not known and is not part of standard physics. Dark matter outweighs normal matter by a factor of 6 and binds galaxies and clusters and stops them from flying apart, as well as causing the expanding universe to decelerate for most of the first 2/3 of its existence. Dark energy dominates dark matter by a factor of 3 and has caused the cosmic expansion to accelerate in the most recent third of the universe's existence. Dark matter and dark energy don't interact strongly with normal matter like the atoms in our bodies, so stealth and cunning must be used to ensnare them and measure them. In both cases, the laboratories used are rich clusters of galaxies, consisting of thousands of galaxies moving swiftly under the action of gravity, and a huge cloud of superhot gas, so energetic that it emits X-rays. Emits X-rays, period. In 2006, an object called the Bullet Cluster was used for a convincing demonstration that dark matter actually exists. In the Bullet Cluster, a bullet-shaped cloud of 100 million degree gas is produced by a high-speed collision between a large cluster and a smaller one. The hot gas was slowed by the collision due to a drag force analogous to air resistance. By contrast, the dark matter hardly interacted at all and sailed through during the collision, ending up on either side of the hot gas. This result would not have occurred unless weakly interacting dark matter dominated the mass of both clusters. In particular, alternate theories of gravity, conjured up to avoid needing dark matter, fail to explain the observations. It seems we have to live with dark matter. Dark energy is even more ephemeral, announcing its presence and ubiquity only by the effect it has on the cosmic expansion. The long and hard search for independent evidence of this existence settled on clusters of galaxies. In a study that took nearly a decade to complete, researchers showed that rich clusters suffer from arrested development. It's more difficult for clusters to grow when space is being stretched. By comparing the size and age of clusters with simulations of how they should grow under different conditions of cosmology, the results cement the interpretation of dark energy as a universal repulsive agent. They also rule out alterations to gravity theory and confirm that general relativity is a good description of the behavior of matter and radiation on large scales. The enigma of dark energy has not been solved, but its status as the biggest challenge in both physics and cosmology has been enhanced. Whether it is a black hole devouring a companion, massive black holes causing mayhem in the centers of galaxies, or clusters being pulled apart by the accelerating expansion of space, Chandra has provided data to illustrate the violence of the universe we inhabit. A result of these insights is a new sense of the power of gravity. Stars are powered by gravity, and gravity also governs the nature of the most compact and energetic objects we've ever discovered. Dark forces even govern the expansion of the universe. When we think of other worlds, we think of the planets illuminated by stars, where any life that exists is beholden to the energy from the star. But in a fundamental sense, starlight is just the inefficient leakage of radiation from mass energy conversion by fusion. The true source of the starlight is gravity. A star is a gravitational engine. Black holes and neutron stars have no light, but they have intense gravity. While they seem alien and utterly different from our world, given suitable protection or adaptation, living creatures might be able to live near these compact stellar husks, using gravity to power their dreams. And that's the end of that section. Chapter. That's the end of the chapter. And there we go. What are you guys saying? Too many street signs to change? We're too lazy to switch over to metric? Yeah. Yep. People couldn't get used to buying gasoline in liters. Yep. The only thing that stuck metrically in the US was the 2-liter bottle for soda. Yep, you're right. Alcohol is also sold in 1.75-liter containers. Yeah. It doesn't make any sense why metric system just makes more sense. Everything's based on like tens. Our pools are weirder still. A lot of them are 50 meters long and 25 yards wide. Wait, seriously? I have no idea how pools are measured. Like Olympic pools and stuff. Also, teachers grades 1 through 6 have been raised in the English standard system and no idea how to teach using the metric system. Coke Zero here. What's the book title again? Oh, yeah. It's called Dreams of Other Worlds. We've been reading it for a while because it's taken me a long time to get through it. There's a lot of chapters. But I believe we actually only have 3 more chapters. The next one's pretty long. So I'll have to take a look and see if we can get it done reasonably in like an hour and a half, because next week yes, this will work. So next week we will be also doing this time. I started today at 9 a.m. My time, which is an hour earlier than normal, and I have changed the schedule to reflect that. So Olympic length and imperial width. But I've changed the schedule to reflect that, so we're going to be starting a little bit earlier next week, and like we did this week. And we'll probably keep that because my job tends to schedule me at like 11 or 11:30, which means that I can do this and then go to work, and we can get through a whole chapter, which is good. But next week I will be here at, like I said, 9 a.m., which is the time on the schedule right now, so you can check that and it will be accurate for your time zone. But the week after, which is the 31st, it is Memorial Day here, and I have some projects to work on, namely my podcast, and I will be out of town that day because I have gotten my vaccine, and I'm going to see like 4 people who have also gotten their vaccines. So go get your vaccine. But I will not be here on the 31st, but I'll be here on the 24th. And then the couple weeks after that, we will finish up the book. We'll have a chat with Professor Impey and ask him any questions we have about Dreams of Other World. We'll have a good time, chill time. And after that, we're going to start something new. And it's not going to be a book. It's actually going to be a video game. And I think it's going to be really fun. And if you are hesitant, I understand. But we've still got like a month with this book. And then I'm just going to ask you guys to give it a try. We're going to try something new. It's the summer. We're going to try something new, something fun, something different. Oh, Andy Weir has a new book? I never read, what was it? Artemis, I think was his second one. Hail Mary. I'll have to check it out. Yeah, summer book break, Love books, but not Kerbal, actually. We're going to be doing a game called Outer Wilds. It's like a nice narrative game, so I thought it could be interesting. A little more structured than something like Kerbal. I also don't own Kerbal, I don't think, but I own Outer Wilds. Dr. Lynn Jersey can read on Memorial Day. There you go. The face, oh my god. You didn't quite understand why the United States has the most COVID infected and dead in total? I don't know. I mean, it's very possible. I don't know if that's accurate, but the reason our numbers are high is because people really messed up last year. Things opened too fast. People didn't put mask mandates in place when mask mandates should have been in place. And a lot of things were messed up. But it looks like we were on a better trajectory, and we have been for a little while. I'm really hoping we don't mess it up again. So, despite what the CDC says, maybe keep wearing your masks. You know, be safe. I'm still wearing my mask whenever I go out. Yeah, it was a very poor handling of the pandemic in 2020. We're a chubby nation, too. We also tested a higher rate than most countries of equivalent size. That's also a good point. But yeah, just a lot of different reasons. But on that note, everybody go out, get your vaccine if you can. If you can't, stay inside, stay safe. And I hope you have a good week. Thank you guys all for being here. I gotta peace out. But yeah, like I said, I'll be back next week at the same time, 9 a.m. And the rest of the week we have Wednesday amateur astronomy, Wednesday astronomy news, Friday amateur astronomy. And I believe Professor Impey is doing his Q&A tomorrow on YouTube. I'm pretty sure Matthew sent out an email for that. And if not, you can check the YouTube channel, Astronomy State of the Art. And it should be scheduled on there. So yeah. I will see you guys later. Have a good day. Bye.